Hey everybody, welcome back. This is Dave here again. This is the video for chapter 1.4 called Combinations of Functions. We're going to look at a couple different ways to combine functions. And so I've divided the video into two parts. Part 1, we're going to look at how to add, subtract, multiply, and divide functions. And in part 2, we're going to discuss a really important concept called compositions of functions. And that's going to be super important as we get into calculus. So what we're going to do first is look at how to add, subtract, multiply, and divide functions. And so this is just the basic definition. Suppose you have two functions, and suppose x is in the domain of both of them. We can look at adding functions, and essentially this is the notation f plus g of x. That's our functional notation, is just literally adding the two functions together. And you can do the same for subtracting. So again, this is just the fancy notation. This is how we express the difference. And the difference is just taking subtracting the two functions. If you want to multiply f times g of x, functional notation here, f of x times g of x. It's as simple as that. And if you want to divide, you just do f of x divided by g of x. But there's one key part with division, and that is anytime I'm dividing, I'm introducing a new issue with the bottom, with the denominator here. So I need to make sure that my denominator is never 0. So it adds another domain restriction. So the moral of the story, as long as your x value is in the domain of both f and g, so it's a good point for both of them, you can add, subtract, multiply, and divide them, provided with division that it's not equal to 0. And we can create new functions. These new functions have the notation that's written here. So let's do an example of how to work with this. Suppose you have these two functions, f of x and g of x, which I've written up here. We want to find the following functions, a through e, and state their associated domains. We want to find the domain of each. So suppose I wanted f plus g. So again, that's the simplified notation, but the correct notation, or the more thorough notation here, would be f plus g of x. That's the function notation. That's just going to be adding f of x, which is x squared minus x minus 2, plus g of x. So this would be your new function that represents the sum of the two. Now in terms of the domain, so the domain, I'm going to call this d sub a, the domain for part A. Well, you need to look at both parts and see what the allowable points, what the allowable x values would be, and I know that I can't have negatives, so I can't have that. I need to have that 4 minus x is bigger than or equal to 0, which means that x has to be less than or equal to 4. And any other point bigger than 4 is not going to work in that square root. So in the first part, the x squared minus x minus 2 has no domain restriction. So in terms of expressing the domain, I'm going to do it as an interval. So it's going to go from minus infinity up to 4 and including 4. That would be our domain for part A. For part B, if you want to take a difference, we'll do the same thing. We're just going to write g first, and then we'll subtract off the function f, x squared minus x minus 2, and there is your new function. And again, the domain for this, domain for part B, you need to look at the two parts of the function and see what the allowable points would be. This has no restrictions, and this is restricted as it was in part A. So the domain's actually going to be the same as it was in part A for part B. For part C, if we want to take a product, we're just going to write f, which is x squared minus x minus 2, and you multiply by g, which is 4 minus x. Make sure to use your parentheses. The domain here is going to be the same. You still only have the domain restriction on the square root part. Now the division gets a little more interesting. So if we want to find f divided by g, we're going to take f on top, and we're going to divide by g to get our new function here. But the domain here for part D is going to be a little bit different. Notice in my denominator now, my x certainly needs to be less than or equal to 4, but actually x cannot be equal to 4 because you'll get 0, and I can't have a 0 in that denominator. So therefore my domain is going to be minus infinity to minus 4 with an, minus infinity to 4 with an open parenthesis for this domain. And finally, part E, g divided by f. You're going to take g on top, which is the square root of 4 minus x. And we're going to take f on the bottom, which is x squared minus x minus 2. And there's your function. Now the domain is a little bit trickier here. In the numerator, I know that 4 minus x must be bigger than or equal to 0. I can't have negatives in my square root, as we had in all the other parts. So x has to be less than or equal to 4 in the numerator. In my denominator, I want to find out if that denominator will ever be equal to 0. And so the best way to do it is to actually factor. So this is, I can factor this to x minus 2x plus 1. So I know that I can't have x equal to 2, and I can't have x equal to minus 1. Those are the two bad points. So the best way to express this domain is to put all this on a number line. So I know the numerator, I need x to be less than 4. So here would be my value 4. I need x to be anything less than 4. So that would be this side of the number line. But in my denominator, I know that I can't be equal to 2. So I'd have to actually jump 2. And I can't be equal to minus 1. So I'd have to actually jump minus 1. And when I express the domain of the function as a whole, I want to express this interval, and this interval. So my domain for part E would be minus infinity to minus 1, open parenthesis, because you're not including that. Then we're going to combine that, so we use this union symbol from minus 1 to 2, both open because you cannot include minus 1 or 2. And then you have a union from 2, open parenthesis, up to 4, and then we close it. So there's our domain. That's the trickiest part of examples like this. All right, so now we're going to talk about compositions of functions. This is a very important concept. If you remember when we talked about functions in chapter 1.1, I had this conveyor belt picture. And so this represented taking an input, putting it into a function, getting an output. In this section, we're going to actually line up 2 or more of these conveyor belts, and they're going to correspond to different functions. So in this situation, I've got 2 lined up. Suppose my first function, I'm going to call that my function g, and the second machine, or the second function, I'm going to call f. So now you come around and you start to put some things onto the conveyor belt. So you take some input x, and you let that thing run into the conveyor belt, into the function g, and out pops an output associated with that input, and we call it g of x. Fine, that makes sense. But now that g of x is going to get onto the next conveyor belt, and it's going to be inputted into the next function f. And out pops an output associated with that input. And the output we could write as f, the function, evaluated at the input, which in this case was g. Okay. Now, of course, the input that we put in to the function g has to be in the domain of g, and then the output here, in order to put it in the next function, would have to be in the domain here. So there is some technicalities where the domains have to match up. But nonetheless, we end up getting an input x, and we get an output f of g of x after the whole process. Okay. So with compositions of functions, we're actually going to combine this into one conveyor belt, one machine, and we're going to give it a new name. So we're going to take these 2 machines and basically combine them together. We give it a new name called the composition. And the composition we write as f with a little o of g. Now you might say, well, why not g of f? Well, you're always going to actually read this from right to left. So the first function that it goes through is going to be the rightmost function, and the last function it goes through will be the leftmost function. So if it goes through g first, you want to put the g on the right. If it goes through f last, you put the f on the left. All right. So that's called f of g, and that notation is the same as saying f with parentheses g of x. So this notation you'll see a lot in textbooks. I'm not going to use it very much, aside from some examples we're going to do. This is really what we're going to be using throughout the course. Okay, so there's another thing we need to discuss about compositions, and that's this issue of domains and ranges. So in this diagram here, we have a function g. Now g takes elements from its domain, so these are all the allowable inputs, and it drops them into its range. So these are all the possible outputs. So you take an x value here, it's going to give you a y value in the range. F does the same thing. There's an allowable domain. Those are the allowable inputs. It's going to drop you off. These are your possible outputs. When I do a composition, I want to ride the function g, and then I want to ride the function f. So imagine a passenger kind of living over here. So you've got this little guy over here, and he says, you know what? I want to get over here. So this is his destination. He wants to ride the function g first. So he'll input into the function g, he'll become an output of g, and then he wants to ride the function f. But the only way that that's possible is if the function g, the range, intersects the domain. So he needs to actually be in this area of the range of g in order to be able to be inputted into the next function f. So there's only going to be certain people that can do that, certain inputs that can do that from the domain of g. It's going to be a smaller section that will actually be able to be dropped off in this intersection. And then that intersection would then be brought to the range of f, and it'll live in some smaller set within that range. So our compositions are actually more restricting in terms of the domains, because not only do you have to be in the domain of your initial function, but the range of that initial function has to intersect the domain of the second function. And we'll see this as we find domains of compositions. But nonetheless, your composition is going to allow this passenger to go right from here, skip over everything, and fall over here, and that's called f of g. To illustrate how function compositions work, let's look at this basic example. I'm going to give you two functions, f of x and g of x, and we want to find the following compositions as well as the associated domains. So let's start with part A, f of g of x. So this f of g, when I actually ask for f of g as a function, we first want to rewrite it as f of g of x. That's step one. Those two notations are the same, but it's good to write it in the second way. Now, leave f and replace g of x with what it is. So I'm looking at g of x. I'm going to replace that with x squared plus x. And finally, that's going to now be the x squared plus x is going to be the input to my function f. So if you look at your function f, it's going to be 2 times the input, but our input is actually x squared plus x now. And remember, it's 2 times the input plus 1. So we're looking back up at this function, and we're inputting g of x where you see the x, and that's what you have here. So ultimately, we end up with 2x squared plus x plus 1 as my composition in this case. And the domain for part A, d sub a, is going to be minus infinity to infinity. There are no square roots. There's no denominators to worry about. Now, if I did g of f, so this is a little bit different. G of f is going to be the opposite order. So what's going to happen here, you leave g and you put in f. So instead of f, we're going to write what f is. That's 2x plus 1. Now we look at the function g, and instead of the input x, we're going to put an input of 2x plus 1. So we have the input, which is 2x plus 1. That'll be squared. So it's x squared plus the input now in this case is 2x plus 1. And you can see what I'm doing here. I'm taking the structure of g of x, and instead of the x's, I'm writing f of x wherever those x's were. Now you could simplify this by expanding it out, but I'm just going to leave it like this. I'm not super picky about that. The domain, again, is all real numbers, so you can write it as minus infinity to infinity. And finally, g of g. So if you have g of x, we're going to rewrite this notationally as g of x, and instead of, let me get a different color here, instead of g of x, you can replace that with what it is. So g of x is x squared plus x. I'll use a different color. X squared plus x. And now we look at g of x and we put in g of x. So you'll have the structure of g of x is input squared plus input, and your input is x squared plus x. Of course, you could simplify this and everything would be great, but I'm just going to leave it. So this is d of c is minus infinity to infinity. Oftentimes, you might even be asked to do compositions of 3 different functions, which is what we're going to do here. So I give you f, g, and h, and I want to find f of g of h. So we can rewrite this as f of g of h of x. So it stays in that same order. And we're going to take this step by step. I'm going to leave the f of g the way it is, and we'll replace the h with what h is. So that's sine x. Okay. Now we'll go one more step. So you leave the f on the outside, and we're going to take the g of x, g of sine of x, and g of sine of x, you look at g of x, that's x squared, but instead of x, it's going to be sine of x. That represents g of sine of x. And finally, we look to f of x, and we look at the structure of f of x. The structure is 4 times your input plus 2, but our input now is sine of x squared, and you can rewrite that as sine squared of x. So my final answer would be 4 sine squared of x plus 2. If we do it in a different order, say g of h of f, it would look like this, g of h of f of x, and you do it the same way here. So you can see what I've done. I've replaced f of x with 4x plus 2. Then you evaluate h, the function h at 4x plus 2, so that's going to be sine of 4x plus 2. Then you evaluate the function g at sine 4x plus 2, so that's sine 4x plus 2 squared using the function g. Another question that you might come across is involving compositions but going in the other direction. And what I mean by that is I'm going to give you a complicated function and we're going to try to express it as a composition. So in this example, I've got this big g of x. It's the square root of x squared over x plus 1. And I want to express it as a composition of 2 smaller functions. What you can do is recognize that there's an inner function here, x squared over x plus 1. And we're going to let that inner function be equal to little g. That'd be the inner function of my composition. Then there's this outer function, the square root, and that's going to be your f. So notice in my composition, if I let the inner function g be x squared over x plus 1, and I let the outer function f be the square root of x, when I take a composition, f of g of x, you're putting the inner function into the outer function and you'll get precisely g of x. Okay? This takes a little bit of practice to understand how it works, but please check out your homework and let me know if you have any questions. I'll see you in the next chapter.